In this video, we'll be taking a look at balance torques using the PASCO static system. Previous video, we looked at balance torques for parallel forces, but in this go-around, we're going to be looking at non-parallel forces. So to do this, we're going to be exploring a couple different methods. So just like the last video, we're going to be using the balance beam with two of these angle indicators on here. Now for this setup, I'm going to place this assembly off to the left. I guess that's relative on how you're watching the video. And just like in the previous video, these are set up initially such that their initial setting is equidistant from the center. Then what we'll do is we'll take a spring scale, clip it up here somewhere. We'll move this later. And then a pulley right around somewhere down here. Just hook that on there. I've already tied strings to all these. On this string right here, I tied a loop so I can just hang this on the spring scale here. Next thing we need to do is we're going to add a mass and hanger to this side. But I'm going to remove that in order to measure the mass of the entire assembly here. So we got our mass and hangers here. I'm just going to do a 50 gram. Actually, we'll do 2 on there. And then we're going to remove this. I have them placed at the 135 mark. Right. So now I'm going to measure the mass of this assembly here. It's 115.2. And that's in grams. Go. And then we can slip this back on here. So now I need to reset this to the 135 mark, just as it is on the other. Right there. All right. So now as we set this up here, need to move this down. And we need to adjust these so that this string here is vertical with the spring scale and the pulley. And mind you, this is just by eye. It's not going to be exact. All right. So before we go, let's see here. All right. So we're going to try and set the angle indicator to 30 degrees on here while this is level and balanced. So in order to do that, we need to adjust this pulley. And bring the spring scale up or down until it's balanced. That's looking pretty balanced. Right. So The idea is to get this to the marks that I have on the spreadsheet. But if you can just get it on one of them, so we'll start with 40 degrees here. And we need to make sure this is now level. It's really a balancing game. So right there, we'll call it level. No, a little more. Oop. Okay, right there. And so we're at the 35-degree mark. This is vertical, and we can read the spring scale here. It looks like it's right at 1.8 newtons. So for the angle here, changes to 35. And we said the force reading on the spring scale was 1.8. We've already calculated the torque for the right-hand side over here, which is staying constant throughout, and we're just varying the angle. So we got 1.8 here. And see, from here, we can calculate the percent error in our measurement based on how balanced they are. So we got about a 6% error here. So let's try another setting. Let's move this somewhere over here. Back up again. Again. All right. And so right now we're at about the 52-degree mark. And we're pulling about 1.35 newtons. Right, I said 52 degrees. Right here, we're reading 52 degrees. Said 1 point, how many newtons? Yeah, 1.35, not quite 4. Once again, we got even closer to balancing these out exactly. So you can go through and do this same procedure for these different angles, adjusting the spring scale and the pulley position appropriately. The next step now, we're going to remove these. Now let's say we have multiple non-parallel forces instead of just the one here. Well, we can investigate that using this. This is a torque wheel. The way this torque wheel works is we have 3 angle indicators, and they're all placed at different positions around the wheel here. Should find the good spot. There we go. And so the way this works is, depending on which angle the indicator ends up at, the radius reading that you measure is where the angle indicator line is tangent with one of these concentric circles. And then the distance from the center to that concentric ring is your radius. So for this, we're going to need a few mass hangers. just delete these values here. There we go. So on the far left, on this one, I'm going to attach a 50-gram mass. Right. Actually, I forgot. Got to measure it. That's 54.9 grams. Okay. We're going to put a pulley out here. I'm going to wrap this around the pulley. Goodness, having troubles here. There we go. Okay. Then we'll do another mass with 20 grams. Measure that. And 2 is 25 grams. And we will suspend this one just vertically. We'll take our last pulley, place it over there. And we'll do the same thing. We'll put one more 20-gram mass. Scale. And enter it on the spreadsheet. Oops. All right. Then we can attach this. Here. We'll make it 40. So 45. There we go. All right. So we'll let this stabilize and we'll let them reach equilibrium. Right now, it looks like it's stopped moving for the most part. So now we can start taking our measurements and finding out our distances. So if we look at the first one, the SAR M1 with the 50-gram mass, the point at which it is tangent to one of these semicircles is right here, which is halfway between the 36 and 38, I believe, 32, 34, sorry, 34 and 36 millimeter mark. So we'll call that 35 millimeters for D1. Rather R1, 0.035. And continued on the right are the torques after they are all calculated out. So what's nice about this, because the way this is set up, it gives you the equivalent force or torque applied on this circle given this mass. So you don't need to go through and actually find the angle to which it's relative to, because it's translated into a 90-degree, which is really nice. And so for the second one, right here, Looks like we cross tangent at the 18 millimeter mark, which is right there. So for R2, it's going to be 0.018. And then R3, if we look at where we cross tangent to, we're a little bit below the 40. So have a between 38 and 40, but on the higher side. So we'll say 39.5. So now what my spreadsheet's done is it's calculated out all these torques. And so what we should expect is the sum of these two torques, because they're on this half, are creating a torque that is clockwise, whereas this one's creating counterclockwise. The sum of these two should be equal to this. And so if we slide over, you can see T1 is 0.0188, T2 is 0.0044. And if we add T2 and T3 together, we should get a value right here that's close to T1. So we're a little bit off. Probably afford to add a little bit more string here. But that's how you use a static system here to solve for non-parallel forces, balanced torques. Let me know if you found this video useful.